Well, thank you everyone for having me today. Right, so I'm going to talk about what was a subset of a larger project, and really what came out of this is a way to kind of survey our students and get an idea of what kind of approaches and motivations they have in our physics course. It's a little too, I mean, I'm okay if you are okay. Yeah, the colors might be better later on with the lights off. So maybe later on we can turn them off. Right, so I'll go ahead and get started. A little bit of a outline here, right? So first I'll briefly talk about the motivations. You know, it was a big project, but I'm gonna kind of skim over that idea and kind of talk mostly about the methodology and the results from this. But I'm going to talk a little bit about the motivation, why we started looking at what types of students we have in our classrooms. Then I'll touch on the theoretical framework we use, right? Any good physics education research is grounded in some theoretical framework that helps guide what data we take, what questions we ask, and how we analyze our questions, right? How we analyze our data, right? And what I want to highlight is this person-centered approach, and I'll talk briefly about what I mean by that. In summary, it's trying to gather information from individuals and look at patterns across those individuals instead of averaging over individuals and looking at how variables correlate to each other. So if we want to get information about how students are acting in the course, it's good to get information about those individuals themselves, right? So ways to do that kind of research. And then, of course, the methodology. So how do we go about collecting this information? How do we analyze it? And how do we do so in this person-centered way? And then lastly, overall, this project is kind of in two phases. The first part, where I looked mostly at algebra-based studio mode physics, was when it was a big collaborative effort between the University of Central Florida, Georgia State University, and George Washington University, and it was a big part of my dissertation. So a lot of my methods and results and analysis comes from that phase of the work. And then what I did at the University of Georgia is kind of expanded that sample space. So I looked at calculus-based studio mode classes, and also calculus-based and algebra-based lecture mode classes with the same survey instrument. And I tried to improve upon the data processing and the interpretation of my results there. So those are the two phases there. Right, so I'll keep going. And I guess if you have any questions along the way, right, raise your hands and I can try to answer them. Right, so first the motivation. Right, so like I said, this work started out as just a part of a large-scale research project that was a collaborative effort looking at looking at the varying levels of success that institutions have had in implementing studio mode or scale-up courses. And I'm assuming most of you know what those classes are since you have one here, but I don't know, is everybody kind of familiar with what a studio mode class is? No, yes, kind of? Okay, so I'm seeing some shaking heads. Well, real quick, right, these studio mode classes are sort of like flipped classes. So they're more student-centered in the sense that we do more activities and like homework type things inside of class and expect students to read and look at lectures outside of class. And often the physical classroom itself is set up in a way that promotes group work, right? So we have round tables where maybe there's 9 at a table working in groups of 3 each, working on problems. There are TAs and the professors roaming around the class to help out when there are problems, and hopefully there's minimal lecture. The style of classroom is prescribed to have a minimal lecture component to it. It has its roots in small-scale settings, right? So maybe 30, 40 students at most, but work at the University of North Carolina, right, the Robert Buechner, helped scale this up, right, that's the acronym, scale up this studio mode classroom to larger numbers of students. At the University of Central Florida, we had 99 in the classroom, and it worked pretty well. So that's just an overview of what a studio mode class is. So we were looking at particularly algebra-based studio mode classes because, in general, algebra-based students are a third of who we teach, but a much larger percentage of who we study in PER, in physics education research. So it was a initiative to try to look at those types of students more so than we have in the past. Right, and the subset of my research involved what students themselves bring to the classroom. So if you're trying to look at what the varying success levels are of a studio implementation at a university, you can't forget what the students themselves are bringing to the classroom. And what I mean by that is maybe their study strategies, so what metacognitive techniques are they using when they study? Are they asking themselves questions when they learn? Things like that. Or are they trying to synthesize knowledge between their physics class and, say, their chemistry class or their biology class? Things like that for study strategies. Their motivations, so why are they learning physics? Do they think it's important for their career? How does physics make them feel, right? Things like that. And then, of course, demographics. So gender, ethnicity, just their backgrounds. Does that have any effect on how they're interacting with the studio mode course or how they're adopting certain types of study strategies? And then later, right, we of course did a lot of work here, developed a survey, did a lot of analyses. So later my goal was to try to extend this and make this survey a little more efficient and make the analysis method a little more robust when analyzing these student responses in survey form, right? So that's kind of the advancements that I've made since being at the University of Georgia. Okay, so right, that's the motivations. So what is the, oops, kind of skipped into the hidden slides here. So the theoretical framework, what are we working with here? Like I said, any physics education research project, you want to ground yourself in some framework where it's going to help guide you what questions you're going to ask and the way you're going to look at your study subjects and how you're going to look at solving the problems you want to solve. So we wanted to try to classify what types of students we have in our class. So we have to kind of work in a theoretical model where we're considering individual students as individuals, right? So one of these theoretical frameworks that exist in a lot of education research is something called the self-regulated learning perspective. And so what this says is that students are basically autonomous, hopefully, right? So they're making their own decisions. They are able to learn on their own. They're active participants in their learning. So they're going to class, right? They're interacting with the course. They're interacting with the teacher. They're interacting with the material. And they can make judgments and adapt to their classroom or what situations you have if they choose to do so, right? So we may have been in classes and encounter students who do not choose to do this, but they do have the ability to do it, right? And so we have a lot of these different factors adding up to help influence students regulating their learning in a classroom. So this also brings us to what do we look at? What types of variables do we look at then in this self-regulated learning perspective? So what kind of things are we going to try to collect from students? What kind of information are we going to collect from them to kind of quantify or qualify qualities about them that fit in this perspective? So we looked at several things. So cognition, right? So their metacognitive abilities, their problem-solving skills. So what are they doing to study in the classroom? Their behaviors, so their study management, like what's their effort they feel like they're putting into the class? How much studying do they feel like they're doing relative to others? What are they doing to manage their studying? Their motivation and affect, right? So how are they feeling in the course? What's motivating them? Why are they learning physics? Those sorts of things. And then the context, so how they're interacting with the course, which is important. An important part for us is because we're dealing with two different types of courses, or initially with one type of course, the studio mode course, which they're expected to interact with a lot with their students in that class. So we wanted to include context in our theoretical framework here. So we collect these sorts of pieces of information. Some are more important than others, and we'll see that. But right, we get this information from students. And what we do then is kind of try to look for correlations, and these lines are very, very faint on the projector. But we look at how all of these things interact together, get these information from individuals, see how they work together, and build this person-centered approach. So we get this information from all individuals and see what kind of groups or profiles we can build on how students approach a class. So what is a person-centered approach? So a person-centered approach is used to find groups of individuals, but we use that by collecting information on individuals, looking at correlations across individuals. So in this, we have a main assumption here where individuals are considered organized wholes that are comprised of a lot of different characteristics working together to form a functioning system. So in this self-regulated learning perspective, with this person-centered approach, we say students are coming into a classroom. There's lots of contextual features, right? They're interacting in a lot of different ways. They're studying certain ways. They're motivated by different things. But they come into the class and kind of have a certain sort of profile, at least by the end of the class time, right? They've experienced their physics class. They've adopted this sort of learning profile to help them survive in the class, or maybe not, depending on how they do. This is compared to a variable-centered approach where we might collect all this information that helps give us an idea of a student's learning profile, but instead we just look at the relationships across those variables, right? So look for just correlations across variables and not consider answers from individual people. So just as a visual illustration, right? So imagine that we give a survey gathering certain pieces of information from a student. So each student's going to answer, say, a set of questions, and each set of questions corresponds to these three variables, right? So a lot of times when we do psychometric surveys, there's, say, 5 questions that relate to how a student regulates their learning when they study, right? Or 5 questions related to what motivates them in their physics class. So we might take an average of those 5, maybe they're Likert scale questions, right? Like least like me to most like me, something like that. We average those together and get a variable value for that person. And we do that for all students, say up to n. And if we wanted to look at correlations, right, in a variable-centered approach, we'd say, okay, well, I'm going to average all these things together, say in their first variable, and we'll get some average for that variable. And we'll do it for variable 2, and we'll do it for variable 3, right? And we might look at correlations across these things and see if certain ways of regulating your learning correlate with certain levels of motivation, right? So we might do that in a variable-centered approach to an analysis of this type of data. What a person-centered approach would be instead is to give the same survey to students, but instead of looking at how variables vary or correlate across people, we would look how they correlate within people, right? And we would then build, say, some sort of profile on an individual and how these variables correlate. You might do this again with these other students, and what we could do is get up to m number of profiles, right? So m could equal big N, right? Everybody could answer these so completely differently that they're their own group, right? But what we will hopefully see, and often what we do is, right, there are patterns in the way people respond to these questions, and therefore there are groups of people who study a certain way or have certain motivations, and so usually m is a subset of the total number of people, right? And so we kind of can use person-centered analyses, statistical analyses, in order to look at these variations and then compare them across people and look for groups of individuals. That's the main sort of theoretical idea behind the method that's used in this research. Right, so I gave sort of I kind of gave a specific example. But so we could have started with some theoretical test with certain variables we're measuring, but maybe we want to know about someone's strategic self-regulation. So what are their strategies? How are they, what metacognitive techniques are they using in their physics course? How does that correlate with their motivations, right, in the course? And then how does it maybe correlate with their epistemology? So what is their, what do they think the structure of knowledge should be or is in their physics course, right? Things like that. So we want to correlate these sort of psychometric measures of students with each other and see if we can say different groups of individuals. Right, so that brings us to, wait, did I skip something? Oh, no, okay. So, right, we could have some number of profiles of individuals, right? And this work has been done previously in education research. And what has mainly been found is the presence of these 5, what they call learning profiles. So these 5 learning profiles are theoretically coherent, so they make good sense, and they're pretty easily interpretable, and they're kind of matched with what we see in classrooms. If you're an experienced instructor, a lot of these probably sound pretty familiar. And these same profiles, or a subset of them, it depends on how good your survey instrument is, have been found in other studies, and they've been found using various student populations ranging from middle school students up to undergraduates with varying statistical methods. But usually they're still person-centered, so we're still looking at relationships, correlations between variables within people, and then comparing them across people instead of just using a variable-centered approach. So I'm going to go through these really quick. Hopefully these sound pretty familiar, especially if you've been teaching, right? One of the first profile is a strategic profile, and often you'll see me use these abbreviations throughout the talk. So a strategic student would be the typical quote-unquote good student, right? So they are motivated to understand the material, and they are able to adopt different study strategies in order to do so. So they're also very engaged and highly motivated. So they're asking questions of their instructor. They're trying to change their study habits if they need to. They don't feel this class is too hard. They might be struggling a little bit because they're trying so hard to do well, but they're able to adjust if they need to, and they're very motivated. Next is what we call a knowledge builder. And they're actually named after one of the variables that we actually collect from students. And the reason we call them a knowledge builder is that they're still intrinsically motivated, and they're still synthesizing information but within their physics class and across their other courses. But they're a little less engaged with the material compared to a strategic student. So they're not trying as hard, they're not asking as many questions, but they still think that physics is cool, that it's good for their future, and they're trying to synthesize their knowledge. They're just not putting in as much effort. Next is an apathetic student, so that's the quote-unquote poor student, right? They seem unmotivated, they're minimally engaged with the material, so they're not trying very hard, they don't think physics is important. This leads to them struggling, but they're not trying to adjust their study strategies in order to do better, right? Next is a surface student. So they're similar in strategies compared to an apathetic student. So they're not engaging in metacognitive techniques. They're not trying to synthesize knowledge within and across courses. They're just not putting in as much effort or as engaged. But they have more motivations and more engagement than, say, an apathetic student. So they still understand that the course is important. They're just trying to delve in deeply to the material when they're trying to learn it. Then lastly is a learned helpless student. And so what this name comes from, right, is that idea that a person thinks they can't do something, right? So therefore they can't do it, right? They've learned to be helpless, right? They can't do this thing. So it's kind of that idea that a student is trying really hard and they're putting in a lot of effort, but they're not using the best metacognitive techniques to do so. So what that can lead to is them trying really hard and feeling helpless and lowering motivations in the course. So it actually might be a chicken and egg thing, right? So maybe they're struggling really hard and not doing well, or not taking the right strategies that they can, and therefore they get discouraged and have lower motivations, or maybe they had low motivations to begin with, and therefore they are kind of struggling in the course. But either way, we have this profile that's kind of a person who seems like they're trying, but they're just kind of struggling to get through the course or learn in a way that maybe an expert would say would be better. So these 5 profiles have been found before. And so one of the goals was to see if these existed in our students as well, right? So if we do some sort of analysis where we group students, do we see something like this? Do we see something different, right? What do we see? Right, so this brings us to using the profile approach. So how do we do this? So what we need to do, right, is collect information on individuals directly from the students, right? So we need to probe how students are approaching their course and what motivates them directly. And so how we did this was to develop what I call the student characteristics survey. So it's just a survey of for each student to take in their course and ask them, what strategies they're taking, what motivates them, right? Kind of get an idea of these psychometric variables that students have when it comes to their introductory physics courses. Right, so what exactly is this, right? And what methods do we use to find these among our students? And that brings us to, right, our methodology. So how do we what is this survey? And then how do we analyze this data to find these groups? So this is kind of a busy slide and the colors are a little washed out, but I'm just going to kind of go through it like this. Right, so we have the student characteristics survey, and it's a compilation of several sets of items from published and validated studies in science education research. All of the questions, at least the ones represented by these ovals, so each oval here is a published and validated research survey, right? That covers this many variables and is comprised of this many questions, right? So this is called the SPOC, the Student Perception of Classroom Knowledge. Really cool name, right? I was fascinated by the people who are just paid to make acronyms, right? So NASA's got the best people, but this one's great too. So we have the SPOC survey. It measures 5 variables, and these colors should match here. So these surveys probe strategic self-regulatory information. So how students what strategies they're taking and what metacognitive techniques they're using in the classroom. So these 3 surveys cover those. The SPOC has 5 variables covered in it, spanning over 24 questions. So there's not an even number of questions per variable, but it's totaled of 24. Right? And so how we get a value for a variable of a student is we take the 5 questions that they ask, at least initially in this first phase, the 5 questions we ask that say cover this idea of knowledge building, right? And we'd average over those 5 that are answered on a Likert scale from 1 to 5, and we get some rating of a knowledge building per individual, right? This is just an example, right, of a knowledge building question. So as I study the topics in this class, I try to think about how they relate to the topics I'm studying in other classes, right? So I prompt, think about your physics class when you take this survey, right? So they're thinking about their physics class when they take this. And so they would answer almost never up to almost always, right, from 1 to 5. And then answer similar but different questions, so 5 other similar but different questions, and they'd answer, on this Likert scale, we'd average those, and we get some value of knowledge building for a student. So we also ask questions about motivations, right? So what motivates them in the class, and we also asked a little bit. It ended up not being too reliable of a scale, but we took a couple questions from a survey that tries to get the epistemology. So what is students' views of physics knowledge, right, in their class? Do they think it's a set of coherent things that work together, or is it just a bunch of facts that are strung together that I'm supposed to remember on an exam, right? So that sort of dichotomy there, getting a measure of that. So overall, we had 72 questions, and we measured 17 scales or variables. So psychometric. Also asked several demographic questions, like their gender, ethnicity, whether or not they had high school physics experience, what their major was, if they were employed, things like that. So we also asked demographic questions. So yes, very long survey, something I improved quite large to get as much information as we could from students. So we had this survey put together. We gave it to students at 3 universities, right? So, one more slide here. This is just another view of the thing. So I have my 3 categories here. Those are the different colors, the different columns back here. So these 3 here are the same here. This is just a view to tell you how many variables psychometric category that I'm measuring on people. So the total, I had 17 variables to work with in my person-centered analysis that I was going to do later on. Right, so we're looking at how they're regulating their learning, how they're approaching their class, putting in, particularly by effort we meant relative to other students. So we asked them, how much effort are you putting in relative to your classmates, right? So making them judge themselves based on their classmates. Then we asked them how important physics seems to be for their class. Asked them, tried to rate how they felt their features should be important versus instant gratification, right? So a question on there is like, there's a party to go to tonight, and there's a test tomorrow. Like, how likely are you to go to that party instead of studying for your test, right? So this sort of, how much is the future important to an individual versus instant gratification? And then what the importance of learning in the classroom was. And then again, some epistemological measure of the structure of scientific knowledge in the class. So overall, 17 variables we got from this survey. Right. So sample size, what we did is, again, we were only looking at algebra-based studio mode physics classes for introductory physics courses. So this is both first semester and second semester physics. We gave the survey near the end of the semester, so we didn't do any time tracking, right? So we didn't look at if these profiles change over time. That's something we could do later on. What we did is we gave it near the end because we were hoping there's a cumulative effect of someone adopting a particular type of strategy or profile in the classroom based on their experiences up to the end of that semester. So we collected data over 3 semesters here. That's what is represented. Only included those who, of course, completed the survey all the way. There were 2 attention check questions because it was pretty long. So it was just something like select agree. Missed either one of those, we threw them out of the data analysis. And then, of course, only people who consented to have their responses used for research were included. Here, GSU and George Washington University, but total we had 900 usable survey responses to analyze. Person-centered way to look at these responses, right? So for these 900 individuals, we have 17 different variables that are in their introductory physics course. So how do we deal with that? Well, what I turned to was cluster analysis. So what you should see here, this isn't just the projector. You should roughly different colors. Some of the hues might be similar, so they ended up all blue here. For me, this one's purple and this one's red, so I don't know. Right, so by person-centered, right, we want to use the individual responses of people to find groups in those responses, right? So what we do or scales. So here is just a 3-dimensional cut of that, right? So you might imagine that every individual has at least 3 of these variables associated with them, and we can plot them in Cartesian space at least, right? So we have 3 of our dots representing our people, right? So we want to find groups of these people based on their individual responses. So we use some measure of distance, right, between these people and find out if there are any coherent clusters or groups of people in here. So what this analysis does, and hopefully this will work, is turn something like this, right, where everybody is in their own group, everybody is their own person, right, into something like this. Okay, this looks good, right? We're now their own groups. So here we have this red group up here. This, for me, it's green. It's yellow here. This yellow group right here, and a blue group down here. So we're turning this into this. Now, just on the surface, right, there's two main categories of cluster analysis. One is hard clustering. And so what this says is that every individual in my data set belongs to one and only one cluster. Right? So this person should be here because they're most like everybody else in that cluster, and that's it. Right? That's not as attractive as something, say, that we call fuzzy clustering. And what this is that every individual, but with a certain probability. Right? So we're not, and that's, I think, pedagogically meaningful for a physics education research project, right? We don't want to pigeonhole a student into saying they're a strategic student or they're an apathetic student, right? And that's it. What we'd like to say is that the way that you're answering this question seems to indicate to me that maybe you're struggling, right? With some, right? So instead of just being in the red group, right, we might think or might see that this person here is actually 80% likely to be in this group and maybe only 5% likely to be in that group, right? So these are just theoretical, non-meaningful groups, but we might see meaningful ones in a cluster analysis and be able to apply these probabilities to individuals. We might be able to say, oh, we only want to look at people who are this likely to be in a particular group because we don't want to analyze students who are just kind of in the middle on all of these things. We want to make sure that we're only looking at people who are going to, that seem to be acting in a particular way that give us, that are. We ultimately settled on using fuzzy cluster analysis for those reasons. So what are some of the, well, no, let's keep going here with the cluster analysis. So because we wanted it to be more statistical, it's kind of strange to wrap your head around, but right, one of the ways to tell how far apart these data points would be just something like a Euclidean distance, right? So you could calculate the distance between all these points and just ask yourself, oh, which ones are the closest together, right? How far apart? So I want clusters to be compact and separate from other clusters, right? So I could base that on Euclidean distance. So I just use the distance formula for all these scales. Hopefully they're roughly the same dimensions, right, for all these numbers. And I get distances and I calculate my clusters that way. Another way to do this is to do it statistically. So instead of saying how far apart are these in Euclidean distance, I would say, well, how far apart are they statistically? Meaning, if I combine clusters, or if I take, say, if I try to take a yellow guy here and put him into the red, is that going to lower my likelihood function of my probability distribution for all these, right? So is it unlikely that this yellow dot came from this red distribution of people? And if it is unlikely, the likelihood would go down, right? So what we use is a likelihood measure of distance. So basically, if the distance between if combining those clusters would lower our likelihood function, right? So if those people shouldn't be in that cluster, that lowers our likelihood, and so that's not a good combination, and we try a new combination, right? We want to maximize our likelihood statistically that the people from a particular cluster come from the same population distribution, right? That's what we want to find. So we use a statistical measure of distance, and we used a statistical clustering method, a model-based clustering. And really what model-based means is that we're capable of exploring different sets of solutions by constraining the covariance matrix between all of our clusters in different ways, right? So we can constrain several things based on the covariance matrix. Some things like the size of the clusters, so how big they can be, the shape, so not only how big they are, but what are their extents in every dimension, like how big, so is it a sphere, is it an ellipse in 3 dimensions, that sort of thing, or a spheroid, right? And also the orientation, so how are these clusters oriented in our 17th dimensional space, right? So we can let those things vary across clusters, or set them to be equal across clusters, and those are the kind of different models we can apply in model-based clustering. And of course, if we are clustering, we're going to vary the number of clusters, right? We want to see, is one cluster solution best? Well, that's a whole group. Is a 2-cluster solution good? Well, probably, but that's boring, right? 2 clusters is just 2 different types of students. Or is a 3-cluster solution best, 4, 5, 6, and so on, right? So we want to judge that, and how we do that is we use several fit statistics, but the main one, especially when it's usually outputted by this same functions, right, that conduct these analyses, is the Bayesian information criterion. And in my case, it really doesn't matter whether you multiply by a negative sign or not. In my case, the higher this BIC is, the better. And what's important to parse out here is that a Bayesian information criterion is a parsimony measure. Right, so of course, you're going to pick a model that has the largest likelihood. So log L is the log likelihood of all of your data together, the likelihood function that you've said that these number of clusters is best, and it's because all the data seems to point that those people come from those probability distributions that you have separated out by that number of clusters. So we have some likelihood function measure of that. But we're going to penalize this function by this m, which is the number of parameters, right? So the more parameters we put in a model, of course, the better fit we're going to get, because we're taking into account a lot more stuff. So if we keep adding that and adding more and more parameters, we need to penalize ourselves. So we can't want to pick just the most complicated solution. Same thing as the more observations we see, right, the more likely we're going to see a bunch of different things. So we want to constrain ourselves by how large our sample size is. So this BIC, this Bayesian information criterion, is kind of a balance between the most likely distribution of clusters in your data set versus how many parameters you're looking at and how many people you've observed. So it's a parsimony measure. It takes that into account. So we ran this cluster analysis, right, and tried to see what the best solution was. And we looked at a couple other fit measures. But first, I'll talk about what we did, right? So like I said, we had 17 variables to work with, right? 17 psychometric variables. But there's a kind of an agreed upon rule that it's not set in stone, but there's this consensus that the minimum sample size I should have in cluster analysis is 2 to the number of dimensions I'm clustering on. So if I use all 17, I would need about 131,000 students, survey responses from students, which I'm never going to get, right? Especially if I wanted to graduate, right? So what we had to do is, out of those 17 variables, right, we had to pick the ones that were what we considered reliable, right? So there's ways to measure how well you think a set of questions is getting at what you think it's getting at, or at least that they're getting at the same thing, so the reliability of a question. So we wanted to pick the best ones that were most reliable, and we wanted to get rid of any things that seemed redundant. So I had some surveys that, 3 separate surveys that measured the same category of thing, strategic self-regulation, right? So there might be some of those variables in there that overlap significantly. And we don't need to cluster on both of those things if they cover the same sorts of information. So we did a lot of correlational analyses and reliability analyses and came to the conclusion that 8 of these variables were really good, really reliable, and weren't redundant compared to each other, and that the other 9 we wouldn't cluster on. We could still look at later, but we wouldn't use in our cluster analysis because they were less reliable or covering the same stuff that this stuff was, but not as well. Right? So that brought this down to 8. 2 to the 8 is 256. Perfect. Right? So we have plenty of data to do this. Cool. And so these are the list of the 8 variables that we clustered on, which I can talk about more depth later if you'd like to know. So where does that leave us? So we run this analysis. We do the model-based cluster analysis on this 900 students and let's see what we get. So we looked at a couple other fit statistics, not just the Bayesian information criterion. I have a list of a few more here. And what the arrow indicates is what you want that fit statistic to be. An up arrow is you want it to be higher. A down arrow is you want that thing to be lower, right? Just as a fit statistic relative to all your solutions. So within one of the models that had the highest BICs, right? They also varied within that model, but the one that gave us the highest BICs, we compare all of these fit statistics across different cluster numbers, right? So what we see here is that the best combination of all of these, this is the sums of squares within. So basically it's a measure of cohesion of a cluster, so how compact a cluster is. This is the sum of squares between, which is a measure of how far apart the clusters are, right? So you want sums of squares within to be small for a compact cluster, the sums of squares between to be large because the clusters are far apart, right? Across that whole solution. Lastly is this measure, I forgot to change it here. I used to call it S for a silhouette. My reviewers were a little upset with that, with the paper, right? So we even used the actual name, or the name that was kind of it doesn't have a name. It's kind of quoted as this in the literature. This Xi-Beny measure. It is a measure of both cohesion and separation. It's the ratio of cohesion to separation, so you want it to be small. And it also takes into account the probabilities, right, that our fuzzy clustering gives us. So it takes into account that there's different probabilities of cluster membership across individuals. So We want this to be low, we want this to be high, this to be low, and of course this to be high. The interpretability was actually all pretty good. So what you actually see is that kind of an expanding out of all of these profiles until you get to what the best solution, right? We have a dip. We have a dip in our sums of squares within here, a increase in our sums of squared between here, a relatively low xi-beny, and a pretty good BIC. A lot of them are pretty similar, actually. So these were a good measure. And we see that a 5-cluster solution, which is also theoretically has a foundation of being a good solution, is what we see as our best solution in this data. So yeah, that's what we went with. Right? Because now, not only is it supported by the statistics, we have a theoretical model to compare it to that's already been shown in previous literature, that there should be some 5 profiles that have a particular variation of psychometric variables across students. So it gave us something to look at and compare. So that's what I did, right? So I took this 5-cluster solution, and to make sure I was only looking at the people that I really wanted to look at, we applied a 75% cutoff. It was kind of arbitrary. It seemed not too high, not too low. So what we said is that we're only going to look at people that have at least a 75% likelihood of being in any particular cluster. If nobody had this high of a probability of being in a cluster across any of the clusters, we got rid of them from the data analysis. That only left us with about 535, so we took a big hit in N, but we were able to be a little more confident about the results we were going to get. So what did we do? We have these results, right? We have clusters. Cluster analysis, it gives you a number of clusters. It doesn't tell you what they mean, right? So it's just a mathematical tool to group people. It doesn't tell you what those things mean. That's up to the researcher to go and carefully compare variables across these clusters and see what story that they tell us, right? So that's what we did. So we looked at all of the variables and ranked them relative to each other across all of the clusters, particularly the 8, well, all 17, but focused in on those 8 we clustered on, right? The other 9 were kind of a confirmatory comparison. And then we did is compared those to see if they looked like that, right? They looked like those that were in the literature. Okay, so spoilers, we saw the same profiles, right? There was evidence that those 5 profiles did exist amongst our physics students. So what I want to do, and I hope these show up okay, is kind of show you a visualization of what this looks like and try to show you the story, the story the data tells and the interpretations we can make out of this data when we go through and look at these in different cross sections, right? So hopefully, it's really hard to see here. So this is an overview. I have a few of these to show you, and hopefully you can at least see the centroids of these clusters here. So that's kind of what matters the most. But just to kind of get you oriented with what these are telling us is that this is just a cross section of the two variables we looked at for our clusters, right? We have a measure of self-regulation and a measure of question asking. It says low level, but really it's just how much they're asking questions in class. The profiles are in different colors, right? These are just numbered for me. I had to go and figure out that these were these actual learning profiles from the literature, but I had them labeled here for us to help us in with the interpretation. So the centroids of these clusters are plotted along with their 95% confidence intervals, so we can see that we're comparing, kind of doing almost bar chart comparisons across variables here. And the lines here are connecting the centroids to individual data points. Now what you might be saying is, well, these look really close here, and these look really close in this variable, but I'll remind you that all the 8 dimensions are important in clustering, right? So if I replot these in a different cross-section of 2 other variables, two clusters that look close here might look very far apart in another set. So all 8 matter for developing these clusters. So I'll probably speed up a little bit here. So this is just kind of the story that the data tells, right? So I'll kind of go through this quickly here. So we have a measure of self-regulation and a measure of question asking. You see they correlate pretty well together, but we see that up here, the strategic students have high values of both, right? So they're asking a lot of questions and they're regulating their learning a lot. Whereas knowledge-building students, like I said, they're a little less motivated, less engaged, aren't doing it as much, and they're doing it about as much as a learned helpless student is. And then, as you might expect, on the lower end, we have surface students and apathetic students who are on the lower ends here. So I'm keeping track of the relative rankings of these variables across all of my clusters in this table here. So what I can do is change one of these variables. So I'll keep this y-axis as a reference, and I'll change the x-axis to something called endogenous instrumentality. It's a mouthful, but really what it means is it's a utility of knowledge. So how important do students think physics is for their future? And so what we see here is a little bit of shifting, right? That we actually see high levels of this And our strategic students, our knowledge building students, and our surface students, right? So they all think that it's worth it, that it's meaningful for their future, right? Then we have learned helpless students that have moderate levels of this, and there are apathetic students at the bottom, right, who have low levels of motivation, right? This is a motivational measure here. And then lastly, we have a measure called surface approach. It's a little bit of a misnomer. That's what it's named in the literature. What it really means is a lack of regulation. So the higher the reading on this, the more they're struggling in the class, the more they think the class has a lot of information, and the more they're having a hard time keeping up with it. So what we see here is high levels of this in our apathetic students, our learned helpless students, and our surface students, low levels of this in our knowledge builders, and a moderate level of this in our strategic students. My interpretation is that they really want to do well, so they're kind of intimidated by the class. So what we see here, if we keep track of all these, and of course all 8 variables are important, but these 4 help us tell a nice little story, right? Or the data tells us a nice little story, that we have these 5 learning profiles, right? We have a strategic student who's efficient and an active learner. We have a knowledge builder who is a little less motivated, right? They're not asking as many questions, they're not regulating themselves as much. Sorry, they're a little less engaged, but they're just as motivated and they're feeling fine in the class, like they're not struggling. Next, we have an apathetic student, low motivations, low strategic self-regulation, high surface approach. They're struggling with the course. We have a surface student who's not really engaging as much, but they still understand why the course is important, but they're also struggling with it. And last, we have a learned helpless student who's not really applying the things they should, that's affecting their motivation, and they're struggling in the class. So we see these same 5 profiles in our data here. So what are some advancements? I'll kind of run through these. Basically what I did at the University of Georgia is made 3 major advancements. The things I wanted to work on, but the survey's way too long. It's 134 questions, right? I wanted to make it shorter so we can maybe in the end game, other instructors can use this in their classrooms. So I didn't want to make it too long. And lastly, I was a little worried about the sample space. We only looked at studio mode algebra-based students, so I wanted to expand that. And also, averaging over Likert scale items is not the best thing to do. And everybody knows it, but everybody does it, right? So we need to try to make better efforts to not do this sort of thing and use a different type of analysis technique. And I'll go over that quickly. So what did I do, right? So we have all that previous work I talked about is published. It's in a physical review, physics education research, so you can look it up. Myself and my advisor put it out. So we had, this was the overview of the survey before, 130 items, 27 variables, including the 10 demographic ones we were measuring. But again, through that same sort of correlational analysis, we reduced the variable number, and we reduced it to 60 items instead. And we still had 5 demographic questions, but I'm asking them things that I can't easily get from a university, and instead I got demographic information from our university. So if they agree for me to get this information, I just ask the institution what it is, instead of burdening the student with that information. So we were able to make it shorter, which is great. Next, right, so I've been doing this since fall 2016. Based lecture, scale-up classes that are calculus-based. And so overall, I've had about 1,850 usable responses over the past couple years. Right, so the last pesky thing is that before, what I was doing was averaging over Likert scale questions. So what we would do to get someone's measure of, say, like I said, knowledge building, I asked them 6 questions about how they're synthesizing their knowledge within and across courses. They answer this on a Likert scale, so any of these can be 1 to 5. I average those together, right, and I get someone's scale score or variable score on knowledge building, right? So this is what I do. But averaging over ordinal data is not the best thing to do, because when we take averages, what we assume is actually at least interval data. And what I mean by that is ordinal data has a order to it, so hence the name, right? So 1 is lower than a 2, which is lower than a 3, etc. But in ordinal data, we can't make the assumption that the difference between 1 and 2 is the same as the difference between 2 and 3, right? Or the same as the difference between 3 and 4, and the same as the difference between 4 and 5, right? We can't make that assumption, but you make that assumption when you average. So we want a better way to look at this. How we do that is through the use of item response theory. So basically what that does is, instead of averaging out, what we do is we take all of the data and we fit a statistical model and we estimate someone's ability or level on a certain variable by looking at the results of this model. And so what the model really does is it takes not only the responses from one individual on all 6 of these questions, but the responses of all my individuals on all 6 of these questions. Fits a model to it, and we use a graded response model to take into account the ordinal level of the data. A lot of item response theory stuff in PER so far has been dichotomous data, so right or wrong. This is dealing with Likert scale stuff, so 1 to 5. And then we get a set of abilities for each student. And what an ability really means is that if we have someone's ability, we know the likelihood that they're going to pick a particular choice in a Likert scale item. So if someone has high knowledge building, we would expect them to pick more 4s and 5s on all 6 of those questions. Whereas if they had low knowledge building, we would expect them to pick more 1s and 2s, right? So we have certain levels or confidence that they're picking certain choices based on this ability. What this does, right, is this transforms our ordinal level data to interval level data. This is continuous stuff. So we can say that the difference between an ability of 1 and 2 is the same as the difference between an ability of 2 and 3. Right? So that helped a little bit with stuff. Since I'm running low on time, I'll kind of skip some of the bigger details. But what we see in the end is the same 5 profiles. So instead of averaging over these 5 variables, right, and it's now 3 different types of classes. It is now using abilities that we're clustering on, not just averages across our items. We do the same cluster analysis. We see a 5 cluster solution is still the best one. We interpret these, and we get the same exact 5 profiles. So they still show up. We're improving the way we're processing the data, and we're still getting the same result, which I think is a plus. Right? So, and then in the end, you might be wondering, well, how is this useful, right? What sort of things can we learn from these profiles? Well, what we can see here is I did a few tests of association. So basically, these are all categorical variables. So learning profile, are you in one of the 5, right, compared to some other categorical information that we have on you. So I asked students several things. One was their grade expectation. So I asked them, what grade do they expect to get in the course? Right? And so what I saw is statistically, there are significantly more strategic and knowledge building students expecting to get A's, statistically more surface students expecting to get B's, and statistically more apathetic and learned helpless students expecting to get C's. So the profile they're adopting seems to be correlated with how they're expecting to do in the course. Next is course level. So I looked at whether they're algebra-based or calculus-based, and we actually see there's more strategic students in calculus-based classes, and there's more apathetic and learned helpless students in algebra-based classes, which I think is just some research to support what we might see anecdotally, right? Some struggling people in algebra-based courses compared to calculus-based courses. And lastly, not only did I ask if they had high school physics experience, that actually didn't seem to matter too much. I also asked them, did they think their high school physics experience prepared them for college physics? And that seemed to correlate highly with learning profile. So what we saw is that strategic and knowledge building students were more likely to feel like their high school physics experience prepared them for college physics, whereas apathetic and learned helpless students felt that it didn't prepare them for college physics. So in the future, I'm kind of running over here, I want to do some more correlations, right, to see what's going on between learning profile and other measures. One thing we can look at is more demographics, so gender, ethnicity, things like that, whether they're working or not, those sorts of things. Conceptual inventories, so some of you may have heard of the force concept inventory or the conceptual survey of electricity and magnetism. These are first and second semester, respectively, tests that they're standardized, that try to get at how much knowledge a student has learned of that particular course. So FCI is mostly about Newton's laws. CSEM is mostly about electricity and magnetism. And then also I want to look at attitudes. So there's something called the CLAS, which measures students' attitudes towards the physical sciences in different variables, right? So different dimensions of attitudes towards physics. So we want to see if there's correlations there. And lastly, I have zero experience in this, but I'd like to somehow put this data online, let instructors elsewhere try this, have their students take it, and hopefully almost instant feedback, right? So they could have their students, a small class, right, take this survey. They could have the information processed in some way, and I could send it back to them and say, yes, this is your students, and these are the probabilities that they're in these profiles, right? Caution them, don't pigeonhole students, right? Use this as a way to, kind of judge or, get a thermometer of your course and how people are approaching it. And that can hopefully help them kind of tweak things or maybe understand how students are approaching the course at a particular time. So that's what I hope to eventually do in the long run. So yeah, I just want to say thank you, and I'll take any questions. Yeah, so for these results here, I haven't actually done any cutoffs yet. So I didn't do any cutoffs when I did the analysis for the second time. And let's see, your other question. What do you do with people in the center there? I am not 100% sure, right? So there's definitely going to be, well, not definitely. I would assume that, so if someone is straight in the middle, I don't know. As an instructor, my answer would be go and talk to them, right? Go, if you, in the theoretical future, you can get some printout, right, of how a student might be approaching a course, and there's no complete indication of what that student how they may be approaching the course. I would go and talk to them, right, and see like, well, what's going on, or how are you feeling about this course? And that would be my answer, because this wouldn't be an end-all for instructional strategies. It would just kind of be a way to approach looking at a snapshot of your classroom. Mm-hmm. Yeah. Right, that's true. Yeah, I'm not 100% sure how to make this instructionally applicable yet, aside of the fact you're kind of getting an overall look at your classroom. I did end up interviewing students, and I had a pretty good matching rate with what they ended up being in the survey and what they kind of answers they gave me in interviews. But again, yeah, I didn't look at those people who were kind of in between. So maybe it's not too helpful for those, but I think that's just for future me to figure out how you handle those types of students. Right. It's possible, right? So like I said, you could set any arbitrary cutoff you want, right? But you're going to be able to get, of course, it's 5 profiles, so the sum should be up to 1, right? So you get 100%, right? So you get some sort of measure of percentages. So they might be more likely to be in 2 compared to the other 3, right? So you might get, it's hard for me to think of things on the fly, right? But you might have like a 30 and 30% somewhere, right? And so that might be the highest compared to the other 3. And you might be able to say, oh, okay, well, they're most likely over here. Let me go and talk to them and see if that works and ask them what they're doing and try to do that on a small scale. Or, if you have a lot of people who look exactly like that, you can kind of think of how do I nudge them one way versus the other, right? So maybe if they're in between like a learned helpless and a surface, maybe you can think of a way to navigate those